Okay, 2.4. We're supposed to find on number 5 if there's any point where there's removable discontinuity. And the only place that that could happen is if it was just a hole and the graph, the limit from each side approaches the same value. This approaches a different height than this, so it's not here. These two right hand and left hand limits are the same, and so all we have to do is move this point up to there. And so we have to say, let's say at this point, this is our C. G of C needs to be changed so it's equal to either the left or right hand limit, the limit of G at C, G of X as X approaches C, I should say. So this is saying there's a limit here. The left side, the right side and the left side both approach a height. And that's what this is saying. And G of C has to be equal to that limit for this to be continuous through there. And that would remove that. So we need to change the height at C so it equals what the curve approaches from either side at that place. That's what they want you to understand about that one. Number 12, they want us to argue that this one is a continuous using our continuity rules. Well, the idea behind that is we know that x squared is continuous for all reals. The whole number line, there's a x squared and it's continuous. We also know that cosine x is continuous for all real numbers. Cosine just kind of keeps going on and on and on both ways. So therefore, our continuity rules say that the difference between two functions that are continuous over their the intersection of their domains, well, these are all reals, has to be continuous. So therefore, the numerator is continuous for all reals. Okay, now let's look at the denominator. Well, 3 is continuous for all reals, because it just kind of keeps going on, and the cosine, we already talked about it. So these two are, so therefore the denominator is continuous for all reals. Now the only thing we have to argue is that since we have a quotient here, that would be, the rule says that the quotient will be continuous for the intersection of the domains. Well, the domains are all reals, as long as the denominator is never 0. We don't get division by 0. Well, cosine x, since the cosine x is always greater than -1 or maybe equal and less than or equal to 1, then 3 minus plus cosine x is always between 2 and 4, because it could be 3 minus 1 up to 3 plus 1, so that's never 0. So the denominator is never 0, and therefore, since it's continuous always, and this is continuous for all the reals, therefore, and 3 dots like that means therefore the function f of x is continuous for all reals. Okay. And 15, let's see, we're supposed to do a similar argument. Well, e to the x is continuous for all reals. I mean, it's that function. And cosine of 3x is continuous for all reals. The 3 just makes it go faster up and down. And the product of two continuous functions on all reals is continuous for all reals. I didn't take time to write it out, but it's just basically that same kind of argument. We just have to go through the steps. Now this one says, look at this and see what's going on. And I've been thinking about this. There's another way besides the way I showed in class to think about this. Whenever you have absolute value will do nothing as long as the stuff inside is already positive. All of the stuff together is positive, or if it's not. Well, from when x is 2 or greater, it's positive. So I could rewrite this. This might help some of you who are kind of lost on how it is. It would be x minus 2 over x minus 2. The absolute value wouldn't do anything to that as long as x was greater than 2. Because numbers bigger than 2 makes this be positive and the absolute value wouldn't change it. Now if x was less than 2, it would change the sign of this and we'd have x minus 2. It wouldn't change the numerator, but the absolute value would change this to the opposite of x minus 2. Because if I put something smaller than 2, like 1 or 0, this is negative, and the absolute value would change the sign of it. That's what that's saying. And otherwise it's negative 1 when x equals 2. Okay, well this reduces to 1. So this function is either 1 for all the numbers greater than 2, or this reduces to negative 1 when x is less than 2, and when it's equal to negative 1. So it's equal to, it's going to graph, it's going to look like up to 2 on the x. At here, it's going to be negative 1 for numbers less than 2, and when we get to 2, it's still negative 1 because of what they said there. And then after that, it is 1, but not there. So it is not right-hand continuous, it is left-hand continuous because there's a solid dot on it there. So it is right-hand continuous, and it's jump discontinuity. It goes from a specific height to another specific height. It doesn't go to infinite. It's not a whole discontinuity. We could do the same thing for this one. So I'm going to rewrite this as 3 parts here. Now I'm going to factor this numerator, which is x minus 2 and x minus 1. And it would be over just x minus 2 as long as x was greater than 2. The absolute value wouldn't change it. Numbers bigger than that would just do that. Now it would be x minus 2 and x minus 1 over the opposite of x minus 2 if x was something smaller than 2. And it says make it 0 when x equals 2. Well, now this cancels this and we get just f of x equals x minus 1. So if I graph that, x minus 1 goes through minus 1 with a slope of 1 up till we get to 2. So that's what that looks like. This looks like these cancel and I get a negative on this, which makes this one be the negative of x minus 1, which is negative x plus 1. So it goes through plus 1 with a slope of minus 1. But it does that for, the first one was for x is bigger than 2. So it goes this way. This one goes for x is less than 2, which is here. And not this. And then it's 0 right there at x equal 2. Well, this one isn't continuous from the left, and it's not continuous from the right. And because this doesn't fill in either of those. This is what this looks like. Okay?